Okay, then first of all, I would like to thank you for having me here so that I can give you my talk. And my name is Robert Six, and I'm a PhD student of Ralph Korn. And the talk I will give today to you was done in joint work with Ralph Korn and Stephanie Schwa, and it's about a generalized linear model framework for ß-variational-autoencoders based on exponential dispersion families. I will give you a small motivation on what beta VAE are. Afterwards, I will show you the definition of the model, and I will show you some literature and a research question. Afterwards, I will talk about the framework, and I will end my talk with the conclusion and references. Okay, let's start off with the motivation. So what we want to do is we want to find a low-dimensional representation of high-dimensional data, as for example of images as shown on the left. And low-dimensional representations can be used, for example, for reducing the input size of for complex models. So in order to speed up the training, or for example, to visualize the data and to cluster the data, which is important for non-image data. Here now on the left, you have the same image data as earlier, depicted as a tabular format, and then it's harder to cluster this data. For example, if you want to cluster the data to happy faces and sad faces, it's easier if they are plotted. So for non-image data, it's it becomes much more harder to cluster this data. And a standard approach to do this is, for example, the principal component analysis. And the PCA is a linear method which provides the direction with the most variation explained. And what you do is you do a singular value decomposition of your matrix, of your input matrix X. Wait, there it is. Yeah, I already depicted it here so that you have like two orthogonal matrices U and V, and you have a diagonal matrix where the singular values are written on the diagonal. And now, for example, if you want to get the two-dimensional representation, you only use the first two columns and the first two diagonal elements of these matrices. And now, if you want to reconstruct this data, what you can apply is you can apply the first two columns of your vector of your matrix V again in order to reconstruct this data. And now the hope is that this data here on the right side looks as much is hopefully the same as the input data was before. Now, a nonlinear approach for this would be the beta VAE. And a beta VAE has an encoder and a decoder. And what you do is that you apply this encoder to your data. And this encoder is usually implemented as a neural network. And you get your two-dimensional representation this way. And now the decoder takes this two-dimensional representation and reconstructs the image given these two dimensions. And again, the idea is that the output of the decoder should look as closely as the input. And now, if we want to compare these two models, we can do this, of course, by numbers, but I want to compare these models now only by pictures and by some of their aspects. And I want to convince you that the beta VE as a nonlinear model has some kind of advantages compared to PCA. So what I show you here are 4 reconstructions of images, and the original image is always given on the left. So here you have the same image for the PCA and the beta VAE, and the reconstruction of the PCA is now given on the right of this image, and the reconstruction of the beta VAE is also given on the right. And what I want you to notice is that, for example, the beta VAE is able to reproduce sad faces, whereas the PCA doesn't seem to have this property. And another thing that I want you to notice is that, for example, the PCA produces pixels with less contrast. For example, in this picture here, you see that this whole picture is more grayish and there are not very much really white or black pixels, whereas, for example, for the beta VE, we still have very black dots or very white dots in the reconstruction. So it's more sharper. Another way to compare these two models is to plot the latent space. So as I told you before, we can, for example, use a two-dimensional latent space, or we can only use two principal components, and now we can plot these. This does not really tell us much yet, but what we can do now is that we can lay a grid of points over this latent space, and we can reconstruct all of these points that you see. For example, here on the lower left, we take this red point of the space, and now we put it inside of the decoder of the beta VAE, and we will get a picture. The same we can do for the PCA. So now let's have a look at this grid of pictures. And here again, I think these pictures speak in favor for the beta VAE. So because of two aspects. The first one is that the PCA seems to have only a very seems to be only able to produce two features. So it has a small region where the pictures are kind of happy, and then there's a region where the pictures are sad. For the beta VE, we have multiple different regions where different aspects of or different faces are shown. So there are even faces where the person is putting out his tongue, which was also present in the training data, but the PCA decided not to reconstruct this at all. And another thing that I want you to notice is that the beta VAE is producing, remarkably good pictures. For example, here on the top, on the bottom left, this is the red dot on the top left here. So this is a picture that the model actually does not care about. Even in training, he hasn't seen this kind of point before. And even though the model hasn't ever seen this point before, the picture is remarkably sharp. For the PCA, I would say all the pictures still have this grayish touch. Okay, so now let's have a look at the definition of the beta VAE. And so the objective of a beta VAE is a trade-off between reconstruction and regularization. And so what we do have is we have our latent codes here. So this was the latent space representations that I was showing you earlier. So these were the points in the latent space. So we assume these are normal distributed, and then we also have our observations X here. These are our images, so the pictures of the faces, for example. And now what we do with these two random variables, we maximize the objective written below here, which consists of reconstruction and regularization. And Y is the first term, reconstruction. So let's have a look at it. So we have an expectation where what we want to do is the following. We sample a variable Z from a distribution given xi. So we say, please give us a variable Z, so that if we put this sample here inside of our likelihood for xi, we want to maximize this. So the likelihood should become very large. And therefore, we want to maximize the reconstruction. So we want to sample Zs that are very good given our input, so that we can again produce very likely the output. And the second part is a regularization term. So where we have some parameter beta, this is where the name beta VAE comes from, which is greater or equal to 0. And the second part is the Kullback-Leibler divergence, which gives us an intuition of how far these two densities here are apart. So the first density is the density of the normal distribution of the latent codes, and the second density is some prior that we assume, which in this case is a standard normal prior. So, and as we are subtracting here in front, this regularization term is kind of penalizing if these two densities are too far apart, which means the encoder is given the task to make its density look like a standard normal distribution. And this is also one thing that I would like you to notice. So here the parameters of the encoders, these are the weights and biases of the neural network, right? So this phi here, theta. So in this regularization term, only the encoder is optimized, whereas in the reconstruction term, both parameters of the decoder and of the encoder are optimized. So, and in this talk right now, we will have a look at the observation model. So at the distribution that we assume for our inputs. And because what we have done in our talk is that we say, okay, we assume a very general distribution for our x, which belongs only to the exponential dispersion family. Okay, so now I will give you a short, now I will show you the GLM framework for the beta VE, and with this I will derive this framework for you, and then I will show you the main result and an approximation to the objective that I've just showed you earlier. I will give you a short error characterization. I will talk about an initialization scheme, and I will talk about auto-pruning, which in my point of view is a very interesting feature of beta VAEs. It's simply, it's pretty awesome. Okay, so yeah, in a GLM, so what is a generalized linear model? So in a standard GLM, we assume a connection between an independent variable and the mean of the observations. And we do this by assuming for the random component that it belongs to the EDF distribution. So we assume that the variable x, the density can be written as the following form here, given some independent set. Yes. So another thing that we have is we have a systematic component. We say, okay, we have linear predictor. So written as here. So our linear predictor at eta is given by z with the cross product of some psi. And we have a link function where we link these two components together. So we say the expectation of our x given z is given by the reciprocal of some function g of eta. And now what you optimize, what you would optimize in this case here is this parameter psi here. So I want you now focus on the density of this random variable again. So first of all, there are a few parameters that that are of interest for us for our talk later now. So this is what we have here. This theta here, this is the location parameter. Another thing that is important for our talk later is this function f here, which is also called the log partition function. And the last thing that is important for us is here var phi, which is also called the dispersion parameter. The function k that is also here, you can ignore for now because it is of non-interest for us in this talk. Okay, so as I said to you, we derived a GLM framework for beta VAE, and now we will talk about this. So as you recall, beta VE has an encoder and a decoder. And now what we do is we split the decoder apart, and we say that M here, this M here, this is the last, I'm sorry, here. This is the last activation of our neural net implementation. So actually we say M here is a function of R to R, and we apply it element-wise. And now we say our systematic component is the part of the decoder that maps from our Latin codes to the output, but without the last activation function applied. And we call this now the systematic component. And the link function, actually, we use this last activation function for this. So what we could say is, we say the reciprocal of G is equal to our last activation. And for the random component, we assume again that we have an EDF distribution. And now, as it holds for EDF distribution, one can show that, for example, the first derivative of the log partition function equals the expectation of x given z. So, for example, if we would choose a Bernoulli distribution for our binomial distribution for our random component, then there is something that is called the canonical link function, or also we call it then the canonical activation function, which in this case would be the sigmoid activation, which you might know from neural network implementations. So this is a very natural candidate for our model. Okay, so given some further assumptions that I just listed here, but don't want to name in detail, we did the following. We derived an approximation to the beta VE objective. So what we did is we had our original objective, and now we have an L hat, which is approximately the same. And as this approximation is quite lengthy, I would refer to our work, which you can see later in references. But nonetheless, I want to give you some very nice features of this approximation. So, and the first feature is that L hat is now deterministic. So I've written up here on the top again this objective, the original objective of the beta VAE. And what you see is that there is an expectation inside of this objective. So usually when you train your VAE, you have to do some kind of, you have to solve this expectation, right? And usually what you do Monte Carlo with one sample, or I don't know. And now for our L hat, this objective became deterministic, so we don't have to approximate some integral. Another nice thing of the approximation is that we can directly derive the maximum likelihood estimates for our encoder model, or for a part of our encoder model. And if we further assume that this first part of our decoder is affine, we can also further derive the maximum likelihood estimates for our decoder. And what can we do? I will quickly drink something. And what can we do given this approximation and also given this maximum likelihood estimates? Well, first of all, we can characterize this error that we make here with this approximation. And so the error depends on the observation model that we choose. So, and here I give you for the Gaussian, the Bernoulli, and the Posterior observation model different error bounds that we calculated. And so what is important is that for the Gaussian case, we have an error of 0, which is very nice, because this shows how our work generalizes existing results. Because for the Gaussian affine model, we can now see that our results are the same as for the results early in literature. And for the Bernoulli affine model, we kind of have the same thing, because if we here we extend, here we show that our work results in the same, produces the same results as some work from us earlier in 2020. And another thing that I want you to notice in this special case is that this error is bounded from below, which means, in fact, that we have here this approximation that we approximate here always from below, which is very nice because, as I said earlier, we want to maximize this objective. And this means if we maximize this here, we also maximize, if we maximize our approximation, we also maximize the original objective, which is nice. Okay, what we also can do, given this maximum likelihood estimates, is we can use these for the initialization of the neural networks. So, and here we consider the Bernoulli observation model. And on the left, we see two cases. We see with the case where we used a ReLU network for our decoder, and where we used an affine network for our decoder. And what we can see is that for the affine model, we see a clear improvement in the convergence. For the ReloNet, we only see a small initial improvement. And what we also see is that the L hat, so this approximation that we can also draw in this picture because we have the maximum likelihood estimates, that this lies below what the beta VAE produces as a loss, which is expected as given by our theory, except for the small initial hinge at the beginning. And so here we have a small burn-in period because some of the encoder parameters are not readily initialized yet. But this vanishes directly after one step. Okay, and another thing that we can do, given this maximum likelihood estimates, is that we can describe the property called auto-pruning, which is inherent in beta VAE. And now this property, in my point of view, is very nice. So let's recall the objective of the beta VAE as given as here. And now when we were optimizing this neural network, in no simulation setup, a network was overfitting, which is usually very troublesome for neural nets, right? So this is what you care really much about. And even for very large values of kappa, and kappa is now our latent dimension, even though if we had synthetic data where we knew we need only a kappa of 2, and we have a beta variation autoencoder with a very high kappa, for example, with 40, there was no overfitting done. And this is the result of the auto-pruning. And where does it come from? Well, it comes from the regularization in the beta VE objective. And simply what this it says is that not needed nodes, and with not needed nodes, I mean the nodes in this bottleneck. So in the example from earlier, this 38 nodes that I don't need because I only have a dimension of 2, these nodes are set to inactive. They are pruned away. And with this, I mean that this regularization term here in the back wins, and that the encoder density is set to the standard normal distribution. And in this case, in the actual implementation of the neural net, the node becomes 0. So no information passes this node anymore. And Burda, Crosser, and Salakudinov in 2016 measure this, the amount of inactive nodes empirically after the training by the statistic proposed as below here. And now what we can do, given our maximum likelihood estimates, is we can calculate this statistic analytically. So using the maximum likelihood estimates, we get the following, we get this expression here. And what do we have here? Well, what is lambda? Lambda 1 to lambda k are the kappa biggest eigenvalues of your empirical covariance matrix. So you calculate your matrix, right? As given, for example, as here. And like this. So, and now what you do is you do a singular value decomposition of this matrix, right? So you have some orthogonal matrix, then you have some diagonal matrix, and then you again have an orthogonal matrix, which in this case is the same because of the structure of S hat. And in this matrix here, there inside are now the eigenvalues, and we take these eigenvalues. We take the kappa biggest eigenvalues. And now what we do is we look if this lambda is bigger than some cutoff term. We say, okay, the statistic becomes this value on the left. If lambda is smaller than this cutoff term, the statistic becomes 0. And this cutoff term here is consists of 3 parts. It consists of the parameter beta, then of our second derivative of the log partition function evaluated at the point 0, and therefore the reciprocal of this, and of our dispersion parameter from the EDF distribution. And what we look here is at the relative part of this eigenvalue, the positive part, the positive relative part of the eigenvalue. Okay, and now what is the benefit of this statistic that we can calculate it analytically? Well, we don't need to train a beta VE beforehand, right? So we can directly say how much nodes are going to get inactive during training and how much are not. And another nice thing is that the effect of beta is directly observable. So I mean, obviously it's a parameter before the regularization term, but now we can directly say what happens if we increase beta. And of course, we also did some simulations for this, and it turns out that our forecasts are quite good for the affine case. So here we have what we analytically forecast, and here's what comes from an affine model after training. So, and as this analytical case is kind of based on the affine case with the maximum likelihood estimates, we are very happy to see it like this. So the pictures resemble each other kind of very much. And above each of these pictures, there's some distance written where you can see how much these are apart. And if this is 0, then this is very good. And if it's big, it's not that good. So, and for the ReloNet case, we see that we still can kind of forecast how much nodes become at least inactive. And what do I mean with this? Well, what we see is that the ReloNet starts to put nodes inactive already when the affine does not yet, for betas for a given level of beta. And we think that this is the case because the ReloNet introduces some nonlinearities in a decoder, so that the decoder needs less units in order to reconstruct good images or in order to reproduce good outputs. And therefore, the net is able to set more nodes to inactive. So what we propose here is that we say, okay, calculate the statistic because it's very cheap to calculate, and you get at least you get an estimate for the ReloNet. You get an estimate of how much nodes are at least inactive. Okay, so now I will conclude my talk. So yeah, I showed beta VAE like PCA are used to represent high dimensional data in low dimension, and I hope you agree with me that they create more meaningful latent spaces than PCA. There is a research area that aims to analyze the beta VAE objective to understand the model better, and our work contributes to this research area. Given the GLM interpretation, we derive an approximation to this original objective, which generalizes the results in literature. And further, we use this approximation to derive maximum likelihood estimates. And we show that the maximum likelihood estimates can be used as initialization for the beta VAE, and also that we can calculate a statistic used to analyze the auto-pruning property of the beta VAE. Okay, and further research aspects in this regard would be to include other EDF distributions in this analysis, for example, the gamma distribution. The gamma distribution is a very important distribution, especially for insurance applications. But unfortunately, we were not able to, let's say, canonically incorporate it into our analysis. And therefore, I would think that incorporating this distribution makes very much sense, and there's a high interest in this. And another aspect would be to consider mixed distributions, because as I said, you only have to have that the observation model comes from an EDF distribution, and now you could think of different inputs where one belongs to a Bernoulli distribution and the other one, for example, to a standard, to a Gaussian distribution. All right, that's it. Thank you very much for listening.
Yeah, thanks a lot, Robert.
Are there any questions?
That's the point. So please ask. until there is a question, let me comment on it. So I'm always impressed if I see that it looks like there is a formal thing. We just have the MLE. We can derive it due to the GLM setting in the family. And then it turns out that there is this auto-pruning property, which is so easy to analyze with the maximum likelihood estimates. So we could analyze it before the training, right? So we don't have to do the training and look then at what got more or less inactive. So does this also help us to design the bottleneck if we know the MLEs?
Kind of. That's a good question. Thank you very much, Ralph. I mean, let's say it as following. It helps you to know what to expect from your bottleneck, right? So if the statistic tells you you should expect 4 nodes to be inactive at least, and none are inactive, you should really start to question your trained net.
Yeah.
So maybe you did some, I hope not, but maybe you did some error in implementing it. Because I mean, this property is inherent in the model, right? So you don't actually have to set it on or off. I mean, you do by this parameter beta, of course, but it just comes for free. And so as I said earlier, you can just have a really big bottleneck and just directly start training. I mean, obviously, it maybe does not make sense out of performance issues. And at some point, you also want to be able to interpret your latent space. So most of the time, 2 or 3 dimensions are also very nice. But nonetheless, I guess the net would regularize itself and then set the nodes inactive that it does not need anymore.
So I thought about like you want to make the bottleneck small. And then you see with the ReloNet, the inequality sign seems to be in the right direction. Yeah, so I'm underestimating the inactive nodes, which means I'm not doing anything wrong if I have the maximum likelihood estimate and then say, okay, we can reduce from 10 to 3 dimensions because we're on the safe side.
Yeah, that's true. The other side would be bothersome.
Okay. Any other question to Robert? That does not seem to be the case. So thank you again. And I'm also excusing you that you have to leave now directly. So that was
sorry for that.
arranged. So thanks for your talk. We will then continue. How is it? We have a break now, right?
I think so, yes.